Hello and welcome back to the last installment of Chapter 8. We're going to talk a little bit about Earth's interior. There's actually quite a lot to talk about here, but for our purposes, we're going to focus on these two concepts and sort of being able to identify and describe wave shadows, and then finally magnetism, which is both interesting because it is related to the behavior of the Earth's interior to the Earth's core, but also generates a kind of magnetic field, something that we're, as scientists and geoscientists, we're not really clear on how that happens, although we have some good models and ideas for that. It also is interesting when you think about how electromagnetic fields are generated by other planets outside of are off of this planet. So, for instance, Mercury has its own electromagnetic field, and so does Mars, but they're much weaker than the Earth's. In general, I want to start out with talking about wave behavior and how waves move through the Earth's interior and why. There are a number of possibilities here for how waves are going to behave, and this is not unlike light waves either. So one option is that they could reflect off of surfaces, and they often do. Reflection usually involves conservation of a lot of energy, and so some energy is transferred into a particular system, but as a wave is generated up here, maybe you have an explosion going on at the surface and it sends waves out. Those waves are going to come down, they're going to hit Earth's boundaries or beds, and they're going to bounce back up to the surface. Okay, that bounce or change in direction is called, here I'll write it out here, is reflection. Okay, and it's one kind of wave response. As the wave comes down, it ends up hitting and then coming up, and at this point we generate a little bit of heat, right? So that's one option, is reflection. The other option here that's pretty common is called refraction. And refraction has to do with the transmission of waves across different beds or boundaries or boundaries in the Earth's interior. So the waves are going to come down and pass through some material, but then they're going to hit a boundary and change direction. One option is that they get steeper, so in other words, they pass through a material, and as they do that, they go from a low velocity zone. So this would be, let's scratch that out for a second. This would be a high velocity. This is all relative, right? And this would be a low velocity material. Okay? So as the waves come down, they get bent and travel at a steeper angle relative to the boundary. Okay, so that's under these conditions where you have high velocity transitioning to low velocity. Where would that happen? Well, let's think about how waves are going to move. Waves move more quickly in a solid and less quickly in a liquid. And we're going to say, let's say, so this was if this was a solid and this was a liquid, that might be a kind of boundary in the Earth's interior for that to happen. Or it doesn't even have to be fully liquid. Could potentially be, it could be partially liquid, a partial liquid. Okay, so that's one response that we might get. If we take this and erase it, another response is to transition in a different way. And so if we have the wave come down like this, and then it is bent more parallel to our bed, in this case, we're going from a low velocity material to a high velocity material. And so this would then, we'd have to change the kinds of materials that we had here. Initially we had a solid going to a liquid, and so what we might just do here is flip that around and go from a liquid to a solid, liquid to solid in Earth's interior, and that's going to bend the waves so that they're more closely parallel to the boundary that they're actually crossing. We can predict this. It's a function of something called Snell's law and the refractive index of materials. We don't have to get into that, or not going to get into that in this course. But if you were interested in exploring this more, that would be Snell's law, SNELL apostrophe S. And so what's interesting is if we look at how seismic waves travel through Earth's interior, there are two things we notice in this particular diagram. The first is that all of these waves, all of these ray paths that are being drawn, let me switch colors here, all of these ray paths that are being drawn here and here, they're all curved. Okay. Well, why are they curved? Well, it turns out that a higher density material is a faster material. So as we go from low to high velocity, remember what happens if we go from a low to a high velocity. The wave passes down and is bent closer to the boundary that it's passing through. Well, if we just increased density, there's actually no boundary in the Earth's interior, but what would happen to the wave is it would do something like this. As density increases, because gravity is pulling on all that mass, we see incremental increases in velocity. And so what happens is the wave actually comes down and bends back up. Incremental changes in direction caused by the density increase in Earth's interior. Now, what happens when waves interact with a big chemical change or a transition from one type of material to another? We see in this case that refraction is occurring here at the core mantle boundary. So waves that are following this ray path skim off the edge of the core and head out to about 103 degrees. So that's an arc degree, okay, which means we're measuring an angle from the focus. So the focus is up here at the top, and that's a degree measurement from the focus down to this line is 103 degrees. Okay, and then we find that those seismic waves actually come back here, and this measurement here is now not 103, it's 142, and it turns out between 142 and 103 degrees, we don't find any P waves, and we don't find P waves because those waves are being refracted, they're being bent towards the core or into the core because we're transitioning from a high to low velocity. Well, why are they being bent into the core like that? Why is the core lower velocity? It turns out that the core is higher density than the mantle, but the outer core is liquid, and liquid is slower material. So when P waves are traveling through a liquid or they're traveling through a gas, they're going to move at a much slower velocity than they're traveling through a solid. And that gives us wave refraction and bends those waves. So the area that is known as the P wave shadow is an area where we don't see any waves, and it's going to occur on both sides of the Earth. So here's 103 degrees again. Remember, that's the angle between the location of the focus, the angle, and the location of where the last P wave is going to come in. And then down here, we get it again at 142. There's our 142 degree angle. Okay, so what's key here is that waves are bent at the core mantle boundary, and they're refracted in a way such that the wave is traveling from high to low velocity material. It's bent towards the core. And so you'll notice that as the wave travels through the core, it actually is curved again. So you get this kind of curved path because the core density is also increasing. Now, what happens when we take our S waves? Well, we see the same situation where we see the last S wave coming into or coming out from an earthquake epicenter out to about 103 degrees. So if we draw our little measurement here, this is 103 degrees from the earthquake epicenter to the core. But what we also see is that the S wave shadow, there are no S waves anywhere between 103 and 103. Or if you want to think about it like this, from 103 to 180. Right, 103 to 180 degrees. So that's on the other side of the Earth. There's no S waves in this area. Well, what happens to the S waves is at the core mantle boundary, they stop. Okay. Now, if you think back, way back a few segments ago, we learned that shear waves, which S waves are shear waves, cannot be transmitted through a liquid. They can only be transmitted through a solid. And that means that probably, as we understand it, what is considered to be the outer core is liquid. So, the P wave shadow is caused by refraction of compressional waves. Compressional waves are capable of being transmitted through a liquid, but they are transmitted more slowly. Okay, even though that liquid is a high density material, the velocity change creates a bend in the wave. It changes its direction, and that means that certain areas of the Earth we will not see waves coming through the Earth's interior. Probably the most important thing to take away from this is that implies that the outer core is a liquid material. Okay, the same issue for S waves. We don't see any S waves passing through to the other side of the Earth between 103 degrees and 180 degrees because shear waves, S waves or secondary waves, all the same, mean the same thing, cannot be transmitted through a liquid. Okay. Now, one of the consequences of having a liquid core is that we think this generates the Earth's magnetic field through the process of convection. The Earth behaves as a dipole where you have a positive and a negative end, and you have field lines exiting the South Pole and coming back into the Earth's North Pole or close to the North Pole. It's a little bit off from the rotational axis. It's called magnetic declination, and it's about 11.5 degrees up at the North Pole. And so this magnetic field has been important and implied that it has helped protect us from solar radiation and from stripping of the Earth's atmosphere, and so has been around for a long, long time. We know from paleomagnetic studies that the actual pole reverses, so we're in a normal polarity. It will actually reverse, and the field lines, instead of coming in at the North Pole and coming out at the South Pole, are actually going to come out at the North Pole and come in at the South Pole at some time in the future, and we call that reversed polarity. What's causing this? Well, we think what's causing this is convection currents within the outer core, okay, as well as potentially some element of rotation in the Earth's inner core. The Earth's inner core is a little bit slower than the Earth's rotation, but it is rotating inside the Earth. But these convection currents are thought to be generating an electromagnetic current, and that any kind of electric current within this liquid metal that's in the Earth's interior is going to generate an electromagnetic field. So, any place you have an electric current, any wire that's in your house is going to be generating an electromagnetic field. And so we think because we have a liquid core, and that liquid core is made of iron, mainly iron and nickel, that it conducts electricity, and that convection creates or along with it being able to conduct electricity, helps to create this polarization in the electromagnetic field that surrounds the Earth. So that concludes Chapter 8, and in this chapter we've covered some elements of the Earth's interior. We also talked about the distribution of seismic waves across the globe, or distribution of earthquake epicenters across the globe. We talked about the different kinds or ways in which we can measure earthquakes, and as well as the different kinds of waves that have been created.